Yeah, hello Kirtana, I'm audible. Yes, Kirtana, can you hear me?
Yes.
All right, let's start the session. Look, in the last class we discussed a little bit about LC oscillations, so I'm going to continue from that point itself. Okay, so if you could remember, we solved one equation for LC oscillations, right? So we got an equation something, if you could remember. The equation was LC oscillations. Okay, so let's analyze this equation in a little bit more detail. If you could remember, I got an equation which suggests that Q is equals to Q naught sine of omega t plus phi. Now the point is how to read the equation. Okay, how to identify what is the current condition. For example, if I gave you a capacitor and inductor, right? How you're going to identify that what is my current situation? What is my start? The start, you know, at generally t is equal to 0. So there can be two cases. I can start my oscillation by keeping my inductor completely charged uh, in the whole energy in inductor, and this is completely discharged, right? Or I can keep it charged, this can be discharged, something like that can happen. So how I'm going to identify? Look, very simple. I gave you an idea. You know, I have to identify the current situation. Look, this is telling what is the charge on the capacitor. This equation is telling you what is the charge on the capacitor, or if you redifferentiate it, you are going to get about the current. Okay, so it will be like current is equals to I naught omega sine, sorry, cos of omega t plus phi. Okay, so if you see carefully, assume that I'm saying that right now I wanted to look at the time t is equal to 0. So you have the equation comes out as q is equals to q naught sine phi, or I is equals to I naught omega cos of phi. This is what I'm going to do, right? Now assume if, so from here you have two cases. If capacitor is charged, fully charged, okay, is fully charged. What does this mean? Then I must be 0. Look, capacitor is completely charged, I must be 0, and Q should be Q naught. This is what I am expecting, right? What does this mean? This means if you put these things in the equation, you are going to get cos phi is equals to 0 and sine phi is equals to 1. What is this case? This can only happen when phi is sorry, so 0, 1. This can only happen when phi is pi by 2, or you can say 90 degree. Understood? So what does this mean? Whenever, so if you just put this value in this equation, so you got q is equals to q naught. When you put the phi value over here, you are going to get sine, sorry, it will become cos omega. This equation is for when you start with, when you start with fully charged capacitor, fully charged capacitor. Okay, if you have doubt like what should I use, I should use cos or what, simply do nothing. It's your choice, whatever you wanted to use. If you want to use sine, you use sine. If you wanted to use cos, you wanted cos. Simply do this. Understood? This phi will take care of the thing. Understood? In one case, you will get phi is pi by 2. In one case, it will be 0 because this is already taken care of. This is already going to take care. So, Kitna, is this clear for you? Any doubt? No doubt, right? Look, now my task is to calculate what I have to calculate. Yeah, time period. So, if you could remember this, how to calculate time period. Time period is nothing but 2 pi by omega. What is omega? If you could remember from the previous class, the omega was equals to 1 by LC of under root. Can you remember this? 1 by under root LC. So this T comes out as 2 pi root LC. This is the time period you are supposed to get. Or frequency from this equation you are going to get 1 by 2 pi root LC. What does this mean? It means to say this circuit, if you Can see this. This is oscillation. Oscillation means to say to and fro. What does this mean? That current is going first. Look, first this is completely charged. The charge is decreasing, decreasing, decreasing. After t time, this charge completely gets stored as a complete energy as a current. Then that current gets start storing as an energy in this. Okay. So this takes time t in the one revolution. So this is what we are doing. I hope this is clear, Krishna. Ketna, is this clear?
Yes, sir.
Okay. If I ask you what can be the maximum current in the circuit, I max. So it's very simple. You know that I is equals to I naught. Look, equation for current is I naught omega cos omega t plus t. I already told you why this 5 we are taking because we don't know what was the condition, how I started my question, what is this question I take. So I'm directly taking this. Okay, very random. This 5 will take care of it. You know that I want I max. This is a constant. This is also constant. What is variable this part? The maximum value of cos of maybe theta is less than equals to 1, less than equals to 1. So you know that I max is equals to I is equals to I naught times of omega. Understood? When something inside this cos theta is 1. Okay. Why this theta? This theta I'm saying is equals to omega t plus 1. Okay. This theta should be something. And actually you know the value of this theta. That is pi by 2 something around it. So I'm really not sure of it. But yes. What is omega? So you can say I max comes out as I by under root L. Look, these things we were supposed to discuss in alternating current chapter, but we are discussing it here. Okay? So we might go back and study that there also, but if you remember this, it's much better. Now let's talk about energy. In the same circuit, if I go here and if you look at this condition, okay, so I'm saying at time t is equals to 0, charge stored is q, okay, and current stored is I. So you know that what is the initial total energy? Total energy. Right now, total energy is basically plus plus minus. So total energy in this is what? Half CV square you can say, or it's better to use what is Q square by C. Okay. This plus energy stored in inductor. What is energy stored? Half L I square. But current is 0, so this becomes half Q square by C. Okay. Q square by C is equals to, yes, this is the only thing here, plus C. If you know after some time, after complete discharge, what will happen in that case? When this capacitor is completely going to discharge, in that case, this complete energy is going to get converted into half Li square because after this, initial energy is this, right? U initial is equals to U final. Finally, you'll be having I square plus what we are left with half. This part is going to 0. So you can simply say if you use this equation, what we are going to get, this current will come out as, this I comes out as something around 2 cancel, okay, this cancel, Q square divided by LC. Okay, anything else is left? Yes, that is under root. So if you put under root, you got current is equals to Q by under root of LC. Something like this. Okay, is that clear?
Yes,
Any doubt witness so far?
no, sir.
No doubt, right? Makes sense. So if you see, let's leave this part for right. If you see actually right now there's no charge left. You have make it 0. Can I say this is the maximum current you can have? So this is I max also. Okay? This is I max you can have. And here it is L max. So you can say the current can actually the maximum current you can ever have is Q by under root of LC. That is, or I by under root by LC. Something like that. So I hope this makes a bit of sense for you. Or Actually here we made a little bit mistake when we were solving this part because this omega is something like this, but something we have made a small mistake over here. Yeah, actually, we made a mistake. The mistake is here. This is Q naught, right? So here it should be Q naught. So this should also come out as Q naught. Okay? That's why I was saying why the equation is not so. And Q naught, you can see the maximum current at the very start. Something like this. Okay? All right. So I hope this is clear so far. So Kirtana, look now. Look right now. If you can see, we have just taken a case. Between case we have taken, right? Between case we have taken. Assume that I have started at t is equals to 0, q is equals to some q, and current is equals to 0. At t is equals to some time t, what is q? Q is equals to some q. I don't know, current is again I don't know. We have to discuss this. So if I just compare the energy using energy conservation, using your energy conservation, you can simply say half q square divided by c comes out as half q square. Look, right now the current left is only q, c is as it is plus. Current is now in the circuit is half by I. Something like this you are going to get. So if you just look at this equation in another way, what you are going to get q square minus this is small q square because you are going to take this other side. So 1 by c is common and this here you are going to get L I square. So what you are going to get I is equals to 1 by LC q square minus q square, okay, under root and under root of this. What is this? This is nothing but omega. So this becomes omega q square minus q. This is very similar to the equation we used to get in case of SHM. In SHM, when your particle was moving, the equation comes out as x is equals to x naught sine something, as if sine omega t plus phi. We used to get this. So when you get the equation of velocity, the velocity equation comes out as v naught omega. So this was actually x naught omega cos omega t plus phi. Also, this equation was also equals to omega. Okay, amplitude square minus x square. So here also what is amplitude? Maximum value of this displacement. Here your I is nothing but what is v? V is dx by dt. Here what is I? That is dq by dt. So here you are getting q square minus this. Q is basically the maximum amplitude of your this charge. Okay. So this is an equation you are getting. Okay. So Kate, look, you will be very clear with the concept if you are good in SHM part. Here I can actually say that if I had to take analogy, if I have to take this x is representing q, current is representing your velocity. Okay, these two things are related for so far. So far, okay. Also, this L is represented. This is basically your inductance. Sorry, this mass here is working as an inductance. That's why, if you could remember, we had something like what is the initial? Sorry, what was the kinetic energy? Look, current is acting as a velocity, right? Charge is particle moving. So you can simply say that it is providing you some kinetic energy thing. Yes. Kinetic energy is basically half mv square. Here what we are writing half L. Instead of mass, we are keeping L. Instead of V, we are keeping I, right? So in electrical. So I hope this makes a bit of the sense for you. Alright, Kirtana, so you are given a circuit right now. I'm just giving you a normal circuit current example. Okay. Keep it as an example one. You are given a very simple capacitor and then you are given an inductor. Okay. This has C, this has L. Assume initial charge is Q. What you need to calculate is find current when charge on capacitor is half of maximum charge. This is what you need to calculate. So Kirtana, calculate it once and get me the answer fast. It's very easy. This problem is very easy. You can actually solve this by using multiple methods, multiple ways are there to solve this. But you just have to get me one of those either ways. Okay, solve it by using whatever the method you remember right now. Kirtana, solve it and get me the answer. Okay, if you can't solve this, I can't help you. Please solve it and get me the answer.
There is a summary 2 by LQ.
Kirtana, first of all, your voice is very low, and actually, I can't get you what you just said.
Is it okay now?
It's fine. It's a bit messy, but okay. What's your answer?
Under root 2 by LQs.
No, it's not under 2 by LQ. Try once, okay? This problem is easy, so I'm giving you more chance to solve it. If you can solve it, much be better.
Sir, is it another 2q by L?
No. Which method you are using to solve that problem? Look it man. This is very easy. Look. You can use energy. You can use the formula we have just studied right now. Okay, the amplitude which I just told you. Also, you can use a normal method. You can calculate the time and something. You can get the answer. Like, yes, actually, you can use either method you want to do. Okay, I'll just give the solution for this and we'll move to the next question. Question says that you have to find the time. Assume at some time at time t, the charge is now q by 2. Q is maximum charge. Okay. You need to calculate current is equals to I. You know very simple that what can be the maximum energy you can ever have? Half q square by c. What energy you will be having at the time when current is flowing I? Half Li square. And the charge in the capacitor is half q square by c. Half Li square plus half q square divided by 4. Actually, when you look at this, 1 by 2 q square by c, 1 minus 1 by 4 is equals to 1 by Li square. So, sorry, it should be L by Li square divided by 2, cancel, cancel. Remove all the 2's from the equation. So, what the answer we are looking at? 3 q square divided by, uh, I think, 4 times of Lc is equals to I square. So, current comes out as 3q by 4 Lc. Okay, let's use another method. What is another method? Current is equals to omega under root q square divided by what is the current q? I is equals to omega. What is that? 1 by Lc under root. What is it? Q square divided by 4. So I is equals to 3 q square divided by 4. These both are under Lc. So this is the answer. Both are same answer. Either way you go, this both are the same answer. Was it really difficult? We got the same answer by using method 1. Method 1, method. What is the difficulty? Just two lines. One, two. Here also, like even though this is a different, but still it also contains just two lines. If you are good at calculations, these kind of problem you are supposed to get in your NEET examination if you are really going for the NEET. And if you spend 3 to 4 minutes, you are good. Okay, so although look at now, this oscillation is basically undamped equation. Okay, this is undamped oscillation. We can discuss it. As far as I know, the NEET syllabus does not cover about damped oscillations, but it may be happen in some cases that you will get some question of the damped oscillation. So I will be discussing about the damped waves. Okay, so damped oscillation can comes up because of the heat energy wasted by via this what I can say resistance. Damped oscillations. else. So what will happen is, now you'll be having a resistance, because you can see there's no case where you can actually waste your energy only by using C and L. So you'll be having R. Basically, what is, when I'm saying resistance, this is not an external resistance. Basically, whenever you put some capacitor, resistance like capacitor, inductor, and wire, each of them has some amount of resistance, right? So we are saying this resistance, either you can say it is external or in the container. Okay, so assume that this resistance is representing this. This is representing just a second. This is representing the net resistance of the circuit. Okay? So assume that initially the charge was Q. At some time, assume some current I is flowing. So I can say that what is the current over there in the circuit? It will look like, um, use this KVL rule. So it will be like Q by C minus L di by dt. Okay, and minus I. This is what we are going to do. Yes. What is Q? Actually, current. Assume that charge is Q. So we have to assume it for, right? Q by C minus plus L di by dt. You know the reason, because charge is decreasing. So we are keeping like this. Minus what is I? This I comes out as dq by dt. Again, that is negative, becomes R plus C. So overall the equation looks like L d2q by dt square plus R times of dq by dt plus q by c is equal to 0. Moreover, you can write it as dq p square plus R by L dq by dt plus q by LC is equal to something like this. You are going to do. Any doubt? Kritima, please let me know if you have.
No.
So look, Kritima, very simple idea is there. If you see this is double differentiation integration. If I go back to a spring case when you had a mass, okay, and it was moving with some velocity v, and there was a case of damping. There was a small damper which was taking its velocity by bv. Okay, it was applying some force bv. So there we used to get an equation because damped it is, right? So there we used to get equation something like dt square, okay, plus b by m we used to get dx by d plus k by m. Now you will say what is k by m and all. This is part from SHM. So if you are good at SHM, then you might be knowing this. If you are unaware of it, so I can't really help. You should actually go and revise the SHM. Okay, this is an indication for you to revise SHM back if you are unaware. So from here you can actually see this is what you are supposed to do. Okay, this is double definition equation. So if you want to relate, you can actually relate it out. So So here actually what happens in these kind of equations, when you solve this differentiation equation, this x usually come out as a e to the power minus, I think it was b t divided by 2. This is the equation we used to get. Something cos omega t plus phi. I'm not forcing you to keep cos here, sine here. This phi will take care of this thing, okay? If you want, you can actually go ahead with sine also. Because I already said this phi is going to take care of that. Understood my point? So in this case, if you see what is b t by m, do I have anything? I don't know. What is b by m? If you see this b by m is nothing but r by l. Yes. So I can say that q is equals to A is the maximum amplitude. So you can call as P. E to the power this. What is B by M? B by M is nothing but R by L. So you can say simply T times of R by L divided by clear? Something like this will do. And sine times of omega t plus phi. You will say, sir, what is omega t? And so you should know that omega is nothing but L by C. Okay, I hope this makes sense. So this should be understood. So this is about the damped oscillations. We don't have to much discuss about the damp. Okay, you can actually just do a redifferentiate. You'll get the current, energy, and everything you can go by using. We can actually get this by using the C. Okay. Also, Ketna, in this case, this omega does not keep constant. This is omega net maximum value. Here, because it is changing, amplitude is changing everything. So omega comes out as this also comes out as omega square minus this is omega naught actually b by 2 and this is what your omega comes out. Sorry, this omega should have changed to very varied value. This happens when you talk about b by m. So what is b by m? That is r by m. Okay. So let's open it once. What is the earlier omega naught? That is 1 by LC square. 1 by R by 2L. This is square. This is also square. So you got something like I think 1 by L square C square minus R square divided by this square by 2L square. So what we got at the end of the day, L is common in both cases, 2 is not common in both cases. So here it will be 2. C is also this. So 2 minus R square divided by 2L square C square. This is the omega you are going to get. Okay, in damped oscillations. So damped LC oscillations. So Kirtana, if you're clear with it, we all that's fine. Then otherwise you can let me know. Is it clear? Kirtana?
Yes.
So how the graph will look like? So, look, we are saying it is oscillation. So in general oscillation, the graph looks like this. Okay, it is never going to end, but it is damped. It means initially you will be having like this, then this, like this, damped, converging at a point, damping. This is A1 amplitude. This is A2. This is A3, and this is A4, and so on. So you can say that A1 is greater than A2 is greater than A3 is greater than A4, and so on. Then it is damped. Okay. If A1 equals to A2 equals to A3 and so on them. You may have a question that is it possible to have a reverse dam that it is starting with this and this is going. So no, it is not. Damping happens because of the lose when it loses its some part of its energy. Okay. Yes, there can be possibility that you're pushing it, you're pushing some energy. Then it can actually happen in a reverse. Okay. After every oscillation, you're providing more energy. It's like for example, there's a person who is swinging. Okay. So he was normally swinging. What you did, you put him more energy. So first time he came till air, but after this, when you put energy, he came till air. Okay. He was supposed to come here. You again put more energy. I'll just take this example. Assume that there was a rod. Okay, it was not moving. Something like that. I'll just give an example. You pushed a little bit. It went this way. Coming this way, you pushed more with more energy. It will come this way. Then it came this way. You applied more energy. So you can say by the time your amplitude is increasing. Okay, but in general, what happens when you when you push, don't put more energy. What air does is, if you could remember, in what air does, you might be reaching here, reaching here, and you stop up. This happens in general case, and this happens when you force, like this opposite thing happens when you force the thing to happen. So yeah, Kate, now let me know if you are clear with the everything. Any doubt? Kate?
No,
Do you have any doubt? Kate?
no, sir.
No doubt, right? Okay, so let's solve one problem. Assume this kind of frame is this kind of frame is this kind. Yes, this kind of frame is given. There is an inductor. It is in a vertical plane. Vertical plane. Something like this is exciting. Something like this. You have a metal ball. This is a metal ball. It has a mass and length. This is a point x is equal to 0. What you did the moment you have released it from here. Look at this. What my point is. You have released it from here. Yes. So yeah, actually you have this related release. So you have to calculate, find the position of rod at any time t. Yeah. Position. This is first thing. Second thing, you have to calculate is velocity of the rod at that time. Third, you may calculate current in the circuit. For all right, so that's the question. Please solve it. Get me the answer. Even if you solve the first part, that is fine. Okay. Yeah. One more thing. I just forgot to tell. There is a magnetic field in this region. Okay. That is B. In a whole complete region. In whole region, magnetic field is there. Okay. Without magnetic field, space no point. Yetna, can you solve this problem? Yes or no, just let me know. If you are not able to, I will solve it.
I'm trying.
Mm, okay, just don't try. Just tell me what is the way how you're approaching this problem. What's your approach behind this? What's your thought process? How you're thinking of thinking for this problem? You're just applying a simple formula or something. You're putting a lot of concepts.
Formulas.
What? Explain me what you're actually doing.
I'm applying formulas.
Which formula you're applying? You're directly applying formula. What you're doing? I just wanted to know that. Just applying the formula won't make any sense. Yeah, okay, no, you're solving it. Okay, look, I don't think you can even solve this, and you are even trying. I don't know because you can't solve this by just putting formula. But which formula you're putting, I don't know. I'll be explaining the position, how you are supposed to calculate the position for this. Okay, so let's go. Look at me. There's a magnetic field. Okay, just think of it. Okay, this is a rod. I'm just leaving this part. I'm saying there's a rod. Okay, look at this. There's a rod. It is falling inside a magnetic field. Can you tell me what will happen with this rod? This rod is falling. Okay, and there's a magnetic field in this region. This is falling downside. So you know if it is falling, what should happen actually with this? Here now look, I can do one thing. I can actually give you one thing to solve this problem. Okay, I just simply look do one thing. When this rod is getting downside, there will be electrons which are moving this side. There will be magnetic field generated this side. This magnetic field will be like this. There will be current flow. this current will be used to magnetic field inside, so we have to use all these methods. Okay, so that's all for this session. Try all these three problems. Okay, these three parts are there. You can try each of them one by one. This is a small hint I have to. One more thing, when this rod is going to flow, it will have some velocity. There will be current flowing just because of this EMF I just told you. Due to this current, there is a current on the rod. There will be force in the magnetic field upside. So keep uh, keep everything in question and solve it. Okay, you'll get the answer. If you have any doubt, let me know. Otherwise, I can have the session guys. Do you have any doubt? The method I gave, just hint I have given. Okay, I have not given a complete solution or something. If the hint is fine, then we can end the session.
Yes.
It's fine, right? Okay. So look, three problems are there for you. You have to solve it by the next day, by the next class. For today's session, that's all for that's all for today's session. Okay, I'm ending the session, guys.